All right, hello. So I want to work through a couple problems that are in our slide deck. We may or may not have gone to them in class. So both of these problems talk about equilibrium and concentration. So what concentrations do you have at equilibrium? This first problem here tells us something about the concentration at equilibrium. So this is what I would call the easy version of this problem. And then the second problem we'll look at doesn't tell us that. It says, here's the Kc, find the values at equilibrium. So that's a little more challenging. So why don't we start with this problem? So whenever we see a problem like this, we're going to want to write a rice table. Now, whether or not I give you the format for a rice table, depending on how generous I'm feeling, but you should intrinsically want to make a rice table. So what's a rice table? We have our reaction, our initial concentration. These are going to be in molarity. Our change in concentration and our concentration at equilibrium. All right. Remember that our equilibrium concentration is going to be our initial plus our delta. All right. Do note that these are always in molarity. So to use a rice table, it has to be molarity. If you're given these in micromolar, millimolar, some other unit of concentration, you have to convert to molarity because your K value is defined using molarity. Now I'm wondering if that matters for this because we're not solving, we don't use Kc, we solve for Kc. So here it might not matter, but if you're solving, when you solve for Kc, you have to use it. And if you are given Kc, you have to use molarity. All right, so it's safer to always use molarity for these equilibria problems. If we're using Kc, if you're using Kp, you're going to want to use pressure, right? All right, so let's look at this problem. We have this reaction up here, which did not survive the export to PDF, so it got chopped down there a little bit. There's something about Lexend with occasionally it looks fine on the slide, and then when I export it, it gets messed up. All right, so we have our balanced chemical reaction. We're going to put that at the top of our table here. I have pre-filled that for us. We're told some information. So we have our initial concentration of nitrogen monoxide. We're also told the equilibrium concentration of nitrogen monoxide. So let's put those on our table. We have 0.260 molar and we have 0.161 molar at equilibrium. I don't have to put the M's into my table. Again, because they are over here, doesn't matter. We're told our initial concentration of H2, right? So that's going to be 0.130 molar. We're not told our initial concentrations of water and nitrogen, our products, but if we're not told them, it's safe to assume they're zero, all right? So when we're looking at this, our very first question should be, what direction is this reaction going to go? Is it going to make products or reactants? Typically, when we make that decision, we compare our Q value versus our K value. Because we have zero product here, our Q value is going to be zero, right? Q is our products over reactants. It's our Kc, but with our concentrations we have instead of our concentrations at equilibrium. So because Q is zero, K has to be positive. K always is positive. It has to be greater than zero. So because Q is zero, it's less than K. It doesn't matter what K is. So this is going to form products. And hopefully that makes sense. Like our reaction can't go backwards if there are no products because there are no products to react. So our reactants react, they make product. So now that we know the direction that this is going to make products, we can fill in our stoichiometric changes, right? So our changes in concentration, we could at this point figure out what that is, but we're going to write this out formally. So we're going to write out our reactants are going to decrease by some stoichiometric amount, and our products are going to increase by some stoichiometric amount. So when I say amount, that's just filler for X, right? So we're going to lose 2x of these. We're going to lose 2x of these. We're going to gain 2x of water, and we're going to gain 1x of nitrogen. And then we can write in our equilibrium values here. So here we're going to have 0.130 minus 2x. We're going to have 2x, and we're going to have x. So in order to solve for x, because we were told the equilibrium concentration of nitrogen, this is actually easy to solve. So we can just look at this information here and say, okay, so 0.260 molar. I'm just going to run in space. I'm not going to write the units. Minus 2x is equal to 0.161. You know, what does that give us? I'm going to do this in 2 steps. 0.260 minus, just to show here that we lose a sig fig when we do this, right? So we get 0.099 is equal to 2x, right? And that's just, we subtract that 0.161 from both sides, and we add 2x to both sides. And then we solve for x. So if I were to do this, I'm going to be honest, guys. I rarely do algebraic manipulations by hand because I'm error prone. So I would turn to Wolfram, or I would turn to Maple in this case after making it this far, right? I would show, okay, here's my setup. I would skip to solving for x. So I like Maple a lot. You guys, it's tedious for you to use Maple to access it, so I don't go over it. Same thing as Wolfram here. I type in my equation, and then I have this extra stuff in Maple to help me solve. If I were to do this in Wolfram, I could just type in that, and Wolfram will tell me that x is 0.0495. Note that Wolfram here is hedging its bet. It's saying it's approximately 0.0495 because Wolfram likes to solve these graphically, so it just approximates your answer. Maple here doesn't do that, but they're going to give you the same answer every time. So that's okay. All right, so we get our x value here is 0.0495. You would also be okay calling it 0.050 if we rounded it to 2 sig figs, which that says we would. That would be acceptable, but no big deal either way. So once we know that that's our x value, we can just go in, do 0.130 minus 2x. Sorry, 2 times is 0.0495. So our equilibrium concentration of hydrogen is going to be 0.0310. Our equilibrium concentration of water is going to be 0.099. I don't love putting the 0 there. We're going to leave it there because we know it's 2 sig figs. Adding that 0 doesn't actually change the value. Screw it. We'll just put it in there. And then our equilibrium concentration of nitrogen is going to be 0.0495. Right, and all of these are molar. So that's actually our equilibrium concentration. I am going to round that because I am showing this as an answer now. So this has 2 sig figs. So we're going to call it 0.050 molar. If I want to be very specific, I can put these little bars over my units to make sure that I am accurately reporting these, right? So all of these are accurate to that 3rd decimal place, and just so happens that that's the 2nd sig fig for each of those, right? Now, if I want to find my Kc, and that should be a capital K, right? Big K. I want to write my Kc expression. So my generic Kc expression for any equilibria reaction is going to be my products raised to my coefficients divided by my reactants raised to my coefficients. So my products are going to be H2O. That has a coefficient of 2. We have nitrogen. That has a coefficient of 1, so I don't have to raise it to anything. We have hydrogen, which has a coefficient of 2, so I'm going to square that. And we have nitrogen monoxide, which also has a coefficient of 2. Now I'm going to plug in my equilibria values here. So we have, right, 0.0990. Remember that in your Kc expression, these values are normalized, so relative to the standard state. So you don't have to write units in here because all of these are divided by 1 molar inside that parentheses. So we have 0.0990 squared. We have our 0.0495. That's not squared. And this is why we're not writing those molars in there, because we'll have weird numbers of molars on the top and bottom. And these are, again, they're all divided by 1 molar to make sure that doesn't happen. We have our equilibrium concentration of hydrogen here. That's squared. And our equilibrium concentration of nitrogen, which is also squared. So now we're just going to put all that in there. I would be careful when you do these to make sure you PEMDAS these correctly, order of operations them, because these are pretty straightforward ones. It's just multiplication and exponentiation that would occur before the multiplication executes. You'll probably be okay. But if you have some like scientific calculator or something that may or may not greatly adhere to PEMDAS, this is where you want to check that before you wreck yourself. All right. And this gives us a nice happy answer of 19.5. Right? Yeah, there we go. So this is one of the problems I wanted to look at. This is the simple version. So in class, we went over this problem, right? And the way we did it in class is actually the hard way. So here we're told the Kc, we're told these initial concentrations of a whole bunch of stuff, right? So we have, is this all 4 of them? Wow, all 4 of them are here. All right, so we went through, we calculated the Q value, we determined that this was going to make reactants, and then we did some math. All right, in hindsight, I realized that I added this extra pip here. So depending on if I saw this in lecture or not, we may or may not have done it with this pip. Notice that that tells you an equilibrium concentration, and that makes this an easy question. So if this looks familiar to you, we skipped that, right? We didn't solve for, like we didn't put this CH4 value down here, did we? We just went through, we solved for these generically, we substituted them into our Kc equation, right? And we solve for X. So we can find X without that information. It's nice that they tell us this, but it was unnecessary. This was a 5th order polynomial, which I guess technically this was a 5th order polynomial, which is obviously beyond our ability to solve by hand, but we have technology, right? We have Wolfram, we have Maple. We don't need this information to solve this problem because we can solve that polynomial by brute force. All right. So we went over the much more complicated version of this in class. You can see the easy solution here. And this just, again, walks through exactly what we did in our previous problem. All right. The only difference here is that we have initial amounts of everything. And the volume of this vessel was 250 milliliters. So we had to remember to multiply all of these by 4 or divide them by 0.25 liters to convert those moles into molarities. All right. So this is the other example question I wanted to go over. This, if we have time, this is another variant of this harder method that we did. This one's a quadratic equation variant. I'm not going to ask us to solve quadratic equations. Honestly, if it pops up, I would still go through Wolfram Alpha. That does not matter the complexity of the problem. Once you have an equality with all your letters in there substituted, take the whole thing, plug it into Wolfram. The fewer intermediate calculations that we do, the less likely we are to have errors, right? So this is a good quantitative method to protect ourselves from making mistakes. All right, so here we have hydrogen reacting with iodine to make hydrogen iodide. Favorable reaction, we can see Kc is positive, which means this will go towards products more so than it goes towards reactants. And we're told initial information, right? So we're told the initial number of moles of H2, the initial number of moles of I2 are mixed in a container of 1 liter. So that 1 liter is nice because that means that these are molarities, right? We would divide by 1 liter to convert moles to moles per liter. Nothing fancy there. So let's get chugging. So we're told that initial concentration of hydrogen, 0.800. Remember, this is molarity, all right? So this is molar. By coincidence of this volume, it works out to be the number of moles present, but we want to be really cautious that we don't just assume the moles present in the problem are the molarity. Next, we have iodine. So the 0.800, same deal. And we're not told how much HI we start with, so we're just going to assume we start with 0. Now, same idea, because we start with 0 product, we know this reaction is going to form products. Doesn't matter what Kc is, it has to. We're going to look at our stoichiometric rates here. We have minus x plus 2x, right? So again, because we're forming products, our reactants are going to go down by their stoichiometric amounts, and our products are going to go up by their stoichiometric amounts. And at equilibrium, we're going to have 0.800 minus x, 0.800 minus x, and we're going to have 2x. Once we've made it this far, we can just plug into Kc, right? So we know our capital Kc is equal to 53.3, and that's going to be on the top. We're going to have products, which is going to be our concentration of Hi squared over our H2 concentration. Notice that I use these brackets for concentration times I2. All right, and we're just going to wiggle this around a little bit. So just so I can have that 53 on the right-hand side. All right, so that's our Kc expression. We know that's equal to 53.3. Somehow we open my pole everywhere. And now we can just substitute in our equilibrium concentrations, right? So we've got 2x, and that's going to be squared, right? Because our equilibrium concentration, let's make this yellow. I don't like that. That's not high enough contrast. Green. There we go. of HI is 2x, so 2x, and then we square that. We're going to have our 0.800 minus 2x. That's going to be to, sorry, not minus 2x, minus x. That's going to be to the first, so we don't square that or anything. Then we're going to have the same 0.800 minus x. All right, and let's just redraw this numerator line. All right, so now we just solve for x, right? So we have a couple options here. We could expand this, make that nice quadratic equation, multiply both sides, to give us a hint for what that would look like. These are really the same thing, so we can combine those into one term, square it. We could have 53.3 times 0.800 minus x squared is equal to 4x squared. If you remember your polynomial math from when we learned this, when do we cover quadratic equation? 10th grade-ish. So 10th grade-ish math. We can square what's inside here. We end up with x squared minus 2 times this thing minus or plus this thing squared times 50, all that. I'm not going to expand that term. Instead, we're just going to take this whole term. We're going to bring it into Wolfram, right? Or Maple or whatever symbolic math software you like. We are going to be careful with our parentheses this time because we do have order of operations. And we're going to remember to, let's see, let me pull this down a little bit so we can see it. Let's pull it down some more. And we're going to remember to put our quality in there, right? So we start with our KC. We have 53.3 is equal to parentheses 2x squared. All right, so make sure you have these parentheses correct, your order of operations. 2x squared does not equal 2x squared, right? Because that's 4x squared. So just be careful of that. Remember your order of operations here. Remember to input these correctly. And this doesn't matter if you're using your calculator or not. You need, input is input. 0.800 minus x. I'm going to write it the way it appears in our initial equilibrium. I could have squared that term too. That's fine. We enter it. It would be nice if Wolfram expanded this into something useful. But notice that it gives us two answers, right? Because a quadratic equation has two roots. So we get our two roots here, and we have to decide which of these is the answer, right? So if I look at my 0.627 here, if I subtract that from 0.8, I get a positive number. That's good. So that's a possible answer. If I look at my 1.1 here, well, 0.8 minus 1.1 is negative. I can't have negative reactants. I can't have negative mass. So this answer is not possible because we're doing chemistry, right? So it's mathematically possible, but it's not physically possible. So our solution here then would be x is equal to 0.628. And it's implied that the answer here is molar, right? Now, we skipped over that functional part. All of these are divided by 1 molar. So I'm going to put that in parentheses. And now we just substitute that into there, right? So 2 times 0. Well, let's do a different color. Let's do green. So 2 times 0.628 molar is going to be 1.26 molar. All right, and that's our equilibrium concentration of HI. So I don't love expanding the quadratics. I don't really love using the quadratic formula. Is it nice to know the quadratic formula? Sure, negative b plus or minus square root of b squared minus 4ac all over 2a, right? Something like that. But I don't think it's really worth our time or our energy or our calculation cost to implement it. So there we have it. 2 different ways of solving Rice tables or using Rice tables to solve equilibria questions. We have the easy variant, that first one where we're told information about the equilibria concentration. We also have the more challenging variant where we're not told those equilibria concentration values. We're told Kc and we're asked to find those equilibria. And we have to back substitute into Kc with those equilibrium concentrations with that unknown change, that x value. Again, these are all related by the stoichiometric changes. So the balanced chemical equation can save us there. That's why we use Rice tables. If you are looking for more information on this topic, you will probably want to search for ICE tables. So ICE without the R, just because the Rice terminology is something that isn't as widespread. All right, so I hope that helps. I hope you take some time, work on some example problems, make sure you're a little confident in this before we get to our exam. So I will see you guys when I see you guys.